Alright, number 10. The fourth term of an arithmetic sequence is 12. Straight away then we know that U4 in an arithmetic sequence can be described as the first term plus 3 of the common differences, and they've told us that we get an answer of 12. Also tells us that the 10th term, which we know can be rewritten as U1 plus 9 times the common difference, is equal to 42. Now if we solve this system of two equations with two unknowns, we're going to end up finding the values of U1 and D. This boxed thing is already the answer to part A. We've written down two equations in U1 and D that satisfy the information. Now we need to solve the equations, and the best way of doing this is with Polysumilt. So in Polysumilt, we'll go to option 2, which is the simultaneous equation solver. Again, we've got two equations and two unknowns. Let's clear what we've got here and enter a brand new system. So we've got 1 U1, 3 D's, and an answer of 12. Then we've got 1 U1, 9 D's, and an answer of 42. Hit the solve button, and we can see that the first variable, which is U1, is equal to -3, and the second variable, in our case is D, is equal to 5. And we've already done number 10. The quickest 8 marks you will ever see. Number 11. Annie starting her first job, she earns $26,000 in the first year, and then her salary increases by 3% every year. So let's think about this then. In year 1, which we can think of as our term U1, she's earning $26,000. In year 2, which we can think of as U2, that $26,000 that she was earning the previous year has been increased by 3%. Year 3, which represents the third term. Whatever she was making the previous year, which was 26,000 times 1.03, is now multiplying another 1.03 because of an additional 3% increase. Or if you prefer, we can say that this is 26,000 times 1.03 squared. By year 4, the fourth term, she'll have her original 26,000, which has now been growing by 3% for the second year, the third year, and the fourth year. That's a 3% increase for years 2, 3, and 4. And lastly, year 5, the one we're interested in, which is like our term 5. Fifth term is 26,000, and then it's increasing by this growth rate of 1.03 over the ensuing 4 years. This is the one we've got to work out. So let's quit and go 26,000 is multiplying 1.03 to the power of 4. And that gives us an answer of 29,263. Is this dollars? Yes, it is. So 29,263.23 to 2 decimal places. We could also round that to $29,263, the nearest dollar, or $29,300 if we were going to 3 significant figures. Alright, Annie spends $24,800 of her earnings in her first year of work. For the next few years, inflation will cause Annie's living expenses to rise by 5% per year. So this is a little bit similar. In the first year, she had to spend $24,800. The following year, because the cost of living has gone up by 5%, she had to take that amount and multiply it by 1.05, and that was what she spent in the second year. By the third year, that previous amount has had to multiply another 1.05. So you can imagine then, by the time we get to the fourth year, that's 1.05 to the power of 3, and so on. Why don't we come up with a general equation for each of these? So the amount that she earns in her nth year of work is her original salary, which is increasing by 3% to the power of n minus 1. Oh wait, let me just think about this. So year 3 meant the third term, and we had the power of 2. Year 4, the fourth term, we had the power of 3. So yeah, it's to the power of n minus 1. So we can see that the exponent is always 1 less. But meanwhile, her cost of spending, I don't want to use a u because I already used a u, so let's use s for spending. Her spending money in the nth year is going to be 24,800 times 1.05 to the power of, again, n minus 1, right? Because in the fourth year, it was to the power of 3. In the third year, to the power of 2. So we need to calculate the number of years it will be before Annie is spending more than she earns. In other words, when is the amount that she is spending more than the amount that she is earning? Alright, one way I can do this is by going to my y equals and putting in each of these equations. I'm going to first put in the Sn, which is 24,800 times 1.05 to the power of x. And then I'm going to put in my un, her what she's earning, which was 26,000 times 1.03 to the power of x. Now, in order for me to be able to see these values on the graph, I have to understand that they're going to start from about 26,000 and then be growing. So as I go to my window, let's make the y-max really quite big. Maybe 40,000. Alright, let's see what happens when I graph this. So there's the amount that she was spending, and there's the amount that she's earning. It's not a very good picture. It looks like there's a lot of action happening in this area. So I'm going to go back to my window, and I'll change my x max to something like 6. Now let's have a look. There's her spending money that's gradually increasing. And now comes her earning money, which we can see starts a little higher, but is soon lower. So let's find the intersection between these two graphs to find out at what point it is that the spending money is more than the earning money. So I can say second calc and go to option 5 for the intersect. Yes, that's my first curve. Yes, that's my second curve, and my cursor's already flashing on what looks to be a pretty good guess. Turns out that they intersect at 2.46 to 3 significant figures. I'll find out that my n value is 2.46. But let's just think about this for a moment. The living expenses and the earning changes don't occur until the end of the year. So although they will be equal to each other at 2.46 years, we have to wait until the end of the third year, and only then will Annie start spending more than she earns. So in fact, n is equal to 3. It will take 3 years. If you had realized this at the beginning, that we were going to have an integer answer, then I suppose we should have gone to the table right at the very beginning and analyzed by comparing these two. After 0 years, the spending money is less than the earning money. Great, she's still making a profit. Come the end of the first year, it's a little closer. Come the end of the second year, it's getting very close. And by the third year, you can see that the spending money has now become greater than the earning money. So if you wanted to use a table method to show your work, I don't know if I'm going to have room to do this, but I'll try. So we'd first have to put in what our two functions are. y1 was the spending money, and then y2. You know when you get that sinking feeling? I'm getting a sinking feeling. I think I've forgotten my functions to put -1s. Give me a moment to check this. Oh dear, I think I did. I'm going to have to do this again. So this was supposed to be an x minus 1. There we go. And down in the other one, shoot, same thing. Sorry guys. So up in the exponent it should have been an x minus 1. Okay. Let's check my table again. So I can see that it's after 3 years she is still spending less than she earns, it turns out that that -1 changed my answer by 1. It wasn't until the 4th year that her spending was more than what she earned. So let's just go back and change this. I think that because I forgot those -1s, this would end up being a 3.46, and this will end up being a 4, so 4 years. And alright, so drawing the table, getting back to the table method, 26,000 times 1.03 to the power of x minus 1. So I've now explained what my y1 and my y2 are going to represent. And now I'll set up a quick little table where my x value, my y1 value, and my y2 value. And so I'll first draw the row where it hasn't quite passed it. At row 3, after 3 years, my spending money still is not greater than my earning money. So you always have to put the row before the passing point. And it was at the end of the 4th year where finally my spending money became greater than my earning money. And that's why, again, the answer is 4 years. Number 12. David invests $6,000 in a bank offering 6% interest compounded annually. Easy. So, I said I wouldn't use that notation anymore, so I'll try to use the IB's notation. So the future value of his money is equal to the current value There we go. Let's fill in everything that we know. So we're looking for the future value of the money. His initial value was $6,000. The interest rate is 6%, so 6 over 100. It's only compounding once each year, but it's going to happen for 10 years. Now that times 1 doesn't change anything in the problem, so as I go into my calculation, I'm not going to bother including it. So 6,000 times 1 plus 6 over 100, all to the power of 10 years. And so his money has grown quite nicely to $10,745.09 if I round to the nearest cent. To the nearest dollar, it would be 10,745. To 3 significant figures, 10,700. Okay, David then withdraws $5,000 to invest in another bank. So if we subtract 5,000 from this amount, the amount that's left in the original bank account is now only $5,745.09. This amount is still going to continue earning 6% interest for 1 more year. And the $5,000 that he's moved to another account is going to be earning 8% interest for that year. So let's add these two amounts together. So we've got 5,745.09 is multiplying 1.06. And to this amount we're going to add 5,000, which is multiplying 1 plus 8%, which I'm just going to write here as 8 over 100. You can of course write it as 0.08, raised to the power of 1, which means I don't need to put any power at all. And the total amount when I add these two things together then becomes 11,489, but it's set correct to the nearest Australian dollar. So to the nearest dollar we get 11,490 Australian dollars.